Good morning. Welcome to another edition of Chemistry on the Fly with Mr. F. Today we're going to talk about water, the universal solvent, at 4.60. Last time we revealed how a pink flamingo could bend water. That was revealed. Today we're going to look at something else. We're going to look at water, the universal solvent. Yesterday, we talked about how we could take water, a glass of water, and we could put salt in it, and that salt would dissolve. And then we could put sugar in it, and sugar would dissolve. And then, lastly, we could put another ionic compound, copper 2 chloride, in water, and guess what? That too would dissolve. So today we're going to reveal how all of that happens. Right, Albert? That's right, because you know what? It's not magic, it's science. Thanks, Albert. Today we're going to look at it by putting a whole bunch of water at the bottom of our screen, and as you can see, we have a lot of water molecules all just kind of floating around randomly in different positions, oriented different ways, and since this is a liquid, the water molecules are going to be moving around quite a bit. And today we're going to start off with looking at an ionic compound. So our ionic compound today that we're going to look at is sodium chloride. Now, here's our sodium chloride atom. Or not atom, it's a lattice, and it's a whole bunch of sodium chlorides all linked together, and we talked about that when we talked about ionic compounds. We're going to look at the sodium chloride lattice, and we're going to see that chlorine, remember this is an ionic compound, so chlorine is going to be a -1, and the sodium is going to be a +1. And I did a little bit of more research and did find that when sodium loses that one electron on the third energy level, the second energy level actually is much, much smaller. So the actual atom appears to be much, much smaller than the chlorine atom. So most of the models that I had seen are actually correct. So we're going to keep that convention here where the chlorine atom is much larger than the sodium atom. We're going to remove one of the sodium chloride atoms from the lattice so we can see it better, and we're going to drop it into the water. Now, once the sodium chloride is in the water, it's actually going to be separated by the water molecules. So they'll actually be able to pull the sodium away from the chlorine. Not only that, but the water molecules will actually orient themselves to kind of guard against the sodium and the chlorine. If we look at this, we can see that we have the sodium is surrounded by the oxygens and the chlorines are surrounded by the hydrogen side. Now I want you to look at this. I'm going to circle the chlorine with all of the hydrogen side of the water molecule. Remember, the hydrogen side has a partial positive charge, and they're going to be attracted to the negative chlorine ion. Now, on the other side, I'm going to circle the oxygen. Now, I want you to see on this screen that I separated the sodium ions from the chlorine atoms, and I also took away all of the water molecules so we can see it better. Notice that they're not combined as salt anymore, NaCl, but they're individual atoms, and they're kind of randomly placed within the whole water structure. Now, this process is actually called dissociation. And dissociation, if we take that out of chemistry, it means to not hang out with other people or other things. If you're dissociated with someone, you're not on good terms with them anymore. And sometimes there's other people in the middle, like water. Water could separate out the two, or keeping the sodium atoms from the chlorine atoms. So sometimes in relationships, there's a third party that does that as well, that helps that causes something to dissociate, or some people to dissociate. So in this case, we have the sodium and the chlorine, and notice that they're all individual on this picture. Now that covers how water dissolves ionic compounds, and salts and the copper 2 chloride would be two examples of that. Now we're going to look at how water, still the universal solvent, takes care of covalent compounds. So we're going to look at a more complex molecule, as you'll see in a second, and it's going to be the glucose molecule. And glucose is C6H12O6. Now, you'll notice that that is all nonmetals. Carbon, hydrogen, and oxygen are all nonmetals, and that makes it a covalent compound. So they're going to be sharing their electrons. Now, I want you to look at something, though. I'm going to circle a bunch of things on the end of this glucose molecule. And it happens that there are 5 things that should look kind of familiar. We have an oxygen with a hydrogen. And what happens there is that oxygen and the hydrogen are actually, just like in water, they're actually acting as a polar molecule or polar part of this glucose molecule. So the oxygen is going to take the electrons or have the electrons a little more often than the hydrogens will. And what would happen when we put it in water, it's actually going to start attracting water molecules that are going to actually be able to separate it apart. Now, if we look at a single glucose molecule, that looks pretty messy all by itself. If you remember, the sodium chloride molecule was nice. It was nice in a lattice structure. It was nice and cubic. It was really nice. Well, the glucose molecule is kind of not so nice. It's in all different planes. It's not looking very nice at all. Now, that's only part of the problem, because when sugar is put together, it actually has all of these glucose molecules kind of all over the place. And so when we put this in water, what we're actually doing is we're going to take away the attraction between the glucose and another glucose, and it's then going to be attracted more to the water. So instead of breaking the whole glucose molecule down, kind of like what we did with the sodium chloride, we actually separate it out into individual glucose molecules. So they're not dissociated like they are with the sodium and the chlorine, where the sodium is broken away from the chlorine. We still have whole glucose molecules here. The carbons are still attached to the oxygens, and the hydrogens are attached to the carbons and oxygens. So they're all still together as whole molecules. So today we revealed that water is the universal solvent. Ionic compounds will dissociate into individual ions, and the covalent molecules will just break apart from each other and dissolve into the water. Right, Albert? That's right. It's not magic, it's science. Thank you, Albert. Well, that's all we've got today, guys, on Chemistry on the Fly with Mr. App. As always, have a great day.